So I guess it's 4 o'clock, and we should probably start to end this conference so I can go home and sleep again. From my point of view, I think we had a good conference. We had some really issues on Monday with people that are speakers that was delayed with flights and so on. But at the end of the day, I only think we had one speaker that canceled all in all, and that was Anton. And he had a very valid excuse because his roof on the house collapsed due to the heavy snow. So I said, you stay home and fix that, and you can come back next year instead. So do I have the slides somewhere? Robin? Not working? So the basic idea, anyway, that we're going to do a small wrap-up here, and we are going to do the Mentimeter thing again. If we get the slides up, so we can get some, quick results on how we actually are doing with the conference. It's good to have technical issues at the end, right? We haven't had it before. Oh, perfect. So the idea is now, most of you have already maybe seen this. So you should supposed to bring up your mobile phone, and then you go to menti.com. And I will do the same, so I see how long time this takes. And then you're entering the code 134725. And we can also see how many there actually is connected to 300 now. So I get the rest of you catch up on this, right? So we're going to do a quick poll. Seems like most people are ready. So the first part of this will be then about the conference itself. The main idea about the conference, the content, the speakers, how we're doing with that. So basically, what is your overall rating of Jfokus this year? What is your general overall quality of the speakers? And general overall the topics. Wow, this is a good way to get in many results because most people don't really respond to the evaluation we're doing afterwards. So the next topic then is how are we doing with food? So how was lunch yesterday? How was lunch today? And what about fikabröd? How was fikabröd? We spent a lot of energy with fikabröd actually. Right size, right taste. We actually, we measure them. Chicken always works, right? And pasta. So, third question on this is, other service around this, how are the house working for us? So basically services, so it would be how has internet worked for you guys? Wi-Fi and internet connection? How was restrooms? Were they clean? Were they nice? Was that working? And service in the wardrobe. Ah, there's a typo. I see. I'm sorry. Thank you for pointing that out. Obvious. And then, the more free. So what can we improve? This is a free text. It takes a little bit longer. I like the quality of the feedback. A lot. Buy horses. I forgot to put in the auto scroll. No, there it comes. More beer. No vegan food. Somebody put in better topic there. So we have an email address here, feedback, so you can then email the topics you want to see next year. Oh, a lot. Thank you very much. And then we do have the love slide. So it is actually working. What are we doing well? Nothing. I like you. I'm married. So this is a little bit of the issue usually. So what happens is that when we do the other form thing, we see that the same topics come up on what we're doing good and think we should improve, which makes it a little bit difficult to handle. Yeah, I like the DJ as well. She was really good. Okay, so with that said, perfect. Thank you very much for the feedback. We'll see what we can work to improve every year. And now we are going to thank you, everybody that are here that makes Jfokus great. So I would like to get most people up on stage. I would like to have the speakers up on stage. I would like to have our stage moderators and our volunteers. But please, guys, you can stay. I mean, the attendees. I see that there's supposed to be something else. So, but partners and attendees can stay. Yeah. And we are all supposed to jump, right? Oh.
Yeah. It has to be height waist.
Whoa.
But this doesn't help.
So this is what it takes to make Jfokus a pretty great conference. Thank you, guys. Thank you. Now it's working. And I also would like to thank all our partners because they are contributing quite a lot, both to the venue itself and what we can do. And I also want to thank you because we always get feedback, both from the speakers and from everybody who's working in the house. They are always nice. You're always asking valid questions, and we get great speakers here because you're actually asking them really relevant questions. So this will be it, I guess, then. So we will have 2 ending keynotes. And we will start first then with, we will welcome up on stage now, Reinhold.
Thank you, Mattias. So, good afternoon, welcome. My topic today is modern Java in an era where change is the only constant. In the past 2 years, we changed the Java platform in 3 ways that we never have before. We took this massive monolithic platform that had grown monotonically over time and sliced it up into 26 standard modules. Second, we removed the Java EE and Corba modules and some other APIs, leaving us with 19 standard modules. And third, we left behind our historically grand and majestic but slow-moving and unpredictable release model, in which we shipped a major release every 2 to 5 or even 7 years. We replaced it with a rapid cadence release model, in which we ship a feature release every 6 months on a strict time-based schedule. Now, modularizing the platform and removing some modules did break a few things. Many have wondered whether the Java ecosystem as a whole will be able to keep up with a 6-month cadence. Taken together, all of these changes are, well, frankly, somewhat scary, but maybe not as scary as you think. Why did we make them? Because adapt or perish now as ever is nature's inexorable imperative, according to H.G. Wells. Or, if you prefer a more modern formulation, adapt or die. So saith Andy Grove. We must change Java in new ways because its competitive environment is very different than it was 20 years ago. There have been 2 big, broad changes. First, many popular platforms now ship new features around once a year, if not every 6 months. If Java is to remain competitive, we must move the platform forward faster. Second, applications are packaged and deployed in different ways than they were 20 years ago. Whether it's the cloud or in packaged apps that are published in app stores, if Java is to remain competitive, we must adapt it to these new environments. Let's look at the first big change, modularizing the platform. This is where we ended up. Nice, clean module graph with 26 standard modules. The base module at the bottom, that's the one module you always need. It's got Java Lang string, Java Lang object in it. The JDK has these standard modules plus many more non-standard modules that contain development and debugging tools, service providers, and various JDK-specific APIs. This pretty picture is not where we started. Where we started was here. A spaghetti bowl of tightly coupled platform components with sometimes surprising interconnections. To print Hello World, you needed Corba. Slicing all this up while maintaining as much compatibility as possible took years of painstaking refactoring and delicate surgery. We were finally able to deliver on that in JDK 9. Now, modularizing an old code base can be a ton of work, but modularizing the platform yielded many benefits. One benefit is that it's more flexible. A module names the modules upon which it depends, so the compiler and the runtime system can ensure the reliable configuration of consistent subsets of the platform. Most applications, after all, don't need all of these modules. If you have an app that only uses the SQL module and the base module, then you can link a custom runtime system that contains just those 2 modules, plus any other modules that they need. The rest of the modules simply fall away. You can package this custom runtime system with your app, resulting in smaller Docker images, smaller App Store packages on the order of tens of megabytes rather than hundreds. To take advantage of this, you don't need to modularize your app. You can do that if you want, and there are many good reasons to do so, but it can be an awful lot of work, and if your app is essentially in maintenance mode, it's probably not worth it. Another benefit of the modular platform is that it's more secure. A module exports the specific packages for use only by the modules that depend upon it. So the compiler and the runtime system can enforce strong encapsulation. How much more secure is it? Of the 6 high-impact zero-day vulnerabilities reported since JDK 7 in 2011, 3 of them would have been prevented if we'd been able to strongly encapsulate the JDK's internal APIs. A final benefit of the modular platform is that it's easier to maintain. The JDK does indeed have many internal APIs, never meant to be used by external code. For decades, we've been warning developers, don't use these. Please don't use these. They've done that anyway, of course, sometimes in some disturbingly popular libraries. Now, to be fair, in some cases, they were after critical functionality that they could get in no other way. So, okay, fair play, fine. But in many cases, frankly, they were just lazy, as we all can be. Why write your own base64 encoder when there's a perfectly good one sitting over in the SunMISC package? Totally unsupported, but it's there. Because of this, for 20 years, we've treated many internal APIs as if they were standard. We've been reluctant to change them because we don't want to break people's code. This has, however, made the platform harder to maintain and harder to evolve. With strong encapsulation, we can close off all access to the internal APIs of the JDK simply by not exporting the packages that contain them. If we did that right away, we would definitely break a lot of existing code. So we're taking a more gradual, nuanced approach, since migration takes time, especially in such a large ecosystem. Starting with JDK 9, and at least through JDK 11, if your code uses JDK internal APIs, then it will not compile, and it may generate warnings at runtime. And by your code here, I mean not just the code that you write yourself, but all those libraries that you pulled down from Maven Central. We have deliberately relaxed the strong encapsulation of legacy JDK internal packages for now at runtime so that old code continues to run. We will eventually strengthen the encapsulation of these packages once we've provided standard APIs for the critical internal APIs and once everyone has had a chance to fix their old code. When we do that in some future release, not very far off, code that uses JDK internal APIs will not run. In the meantime, here's an example of the kind of warning you might see if you haven't seen one of these already. This is the console output of Jython, a Python interpreter written in Java running on JDK 9. Several warning lines here to interpret. First, an illegal reflective access operation has occurred. This is one that will be impossible at some point in the future. The warning identifies the code responsible, and it also shows the internal API that was accessed. It helpfully suggests that you report this error to the maintainers of the errant library so you can do your part to help push the ecosystem forward. It tells you how to get additional warnings if you want to see them, because by default, only the first one of these warnings will be shown. We don't want to mess up your output too much, just a bit, just enough to be annoying. And finally, it reminds you that all illegal access operations will be denied in a future release. To help you get ready for that future when such code will not run, we introduced a new tool in JDK 9 called JDEPS. If you run it against an existing jar file with the --JDK internals option, it can detect most uses of internal APIs. As an example, here it detected the use of sun.security.x509.x500 name, which is indeed a JDK internal API, and it even suggested a standard replacement. You read carefully, that standard replacement has been there since Java 1.4, which was released in 2002. There's really no excuse not to be using it. So the modular platform does break some things, but it doesn't break everything. In fact, if your code uses only standard Java SE APIs, then it most likely will work without change. I say most likely here because there are yet some very minor differences. We removed a few obscure, rarely used methods and mechanisms to enable the clean modularization of the platform. We also made some behavioral changes that honor the specification, but in rare cases might break existing code. If you want to know more, have a look at JEP 261, which lays out all of the compatibility-related changes in great detail. Beyond that, to learn more about Java modules and the modular platform, I can recommend all three of these excellent books. The modular platform enabled the second big change of the past year. We've reduced the platform by actually removing things for the first time in Java's history, or at least, well, the first time on purpose. We removed the Java EE and Corba modules in Java 11. Poof, they're gone. Why did we do this? Well, the details are all in JEP 320, but in a nutshell, these are costly to maintain. They've been the source of multiple security vulnerabilities over the years, and nowadays they're either available elsewhere, as in the case of Java EE, or they're just no longer relevant, as in the case of Corba. We removed some other smaller things too. As I mentioned, in order to modularize the platform cleanly, we removed some fairly obscure methods in Java 9. Most of these are for configuring property change listeners in various core APIs. Frankly, they probably never should have been added in the first place, but there they were. We only removed these after analyzing lots of code out in the wild to see if anyone was using them, which hardly anyone was. While we were at it, we also removed a pointless constructor that had somehow, Brian, snuck into Java 8. We removed more methods in Java 10. All of these methods are ill-defined, actively harmful, don't work, or don't do anything useful. We removed yet more such methods and one class in Java 11. Now, removing things, yes, can cause breakage. So to ease the pain, we always give advance notice by deprecating APIs to be removed at least one release in advance, if not more. As an example of that advance notice, here are all the APIs deprecated in Java 11 for removal in a future release. If you look carefully, you can see that these include many finalize methods sprinkled through the core APIs. We're removing those because finalization is a fundamentally broken mechanism that we have finally replaced with something better. Now, when an API is deprecated for removal, that's always noted in its Java doc. For example, here is a method named trace method calls in the Java-Lang runtime class. This dates way back to before Java 1.0, when all we had were bytecode interpreters. This was an API designed to let you control tracing of method tracing of a bytecode interpreter. As you can see, it says this method was intended to control method call tracing. It has been superseded by JVM-specific tracing mechanisms, also known as JVM-TI. Note the subtle and sophisticated specification, not implemented, does nothing. Few people will miss this method, I suspect. If you compile source code that uses an API that's deprecated for removal, then of course the compiler will helpfully warn you about it. Okay, popping up a level. First we modularized the platform. Then we trimmed it down. And then we started moving it forward at a faster pace with a new release every 6 months. How can that possibly work, you might be thinking? Well, let's look at a timeline. We shipped JDK 9 in September 2017. We shipped JDK 10 just over a year ago. We shipped 11 last September, and we'll ship 12 next month, and so on every 6 months, like clockwork. A feature release can contain any kind of feature, a language feature, a library feature, a performance feature, a JVM feature. It can even contain a feature that removes an old feature. For this to work, a feature can go in only when it's nearly finished, because we can no longer slip a release in order to fix a broken feature. But if a feature misses the current release, that's okay. The next one is only 6 months away. It's not 3 years or 5 years or 7 years in the worst case. At the beginning of all this, of course, was JDK 9, the final massive JDK release. It contained 90 JEPs, 90 major features. We shipped it 3 years and 6 months after JDK 8, which had shipped in 2014. We did that with 2 major slips to the schedule. Now, engineers from Oracle did much of the work shown here, but not all of it. 6 JEPs came from outside Oracle by contributors from Red Hat, Linaro, and SAP, plus a couple of independent folks, Doug Lee and Laurent Borges. These non-Oracle contributions included 3 whole CPU ports, some significant performance work, and a brand new 2D graphics rasterizer. So after all this, and of course, Jigsaw, the module system was in here too. After all this, what was going to be in JDK 10? One worry that we actually had about the 6-month cadence was we might wind up with 0 features in a release. I mean, if nothing's ready, well, the release is going to ship, and well, maybe it's just a bunch of bug fixes and small enhancements. It's theoretically possible for there to be no major features. Happily, that turned out not to be the case. JDK 10 contained 12 JEPs, including 1 language feature, local variable type inference, more performance work, a massive refactoring of the source code into a single Mercurial repository. And again, Oracle engineers did much of the work, but not all of it. 2 JEPs came from other contributors. Roman Kenke of Red Hat contributed a GC interface, and some engineers from Intel enabled heap allocation on alternative memory devices. This pattern continued with JDK 11 last September. There were 17 JEPs in JDK 11, including some long-needed JVM improvements, a brand new HTTP client API, the ability to launch single-file source code programs, which is really handy for quick debugging, and TLS 1.3, just in time for the final internet standard. Oracle engineers did, again, do most of this work, but 3 JEPs were contributed by others. Engineers from Bellsoft and Cavium contributed work on ARM64 performance. Alexei Shibilev of Red Hat contributed the Epsilon garbage collector, a garbage collector that never collects, which is actually useful for some things. And Jean-Christophe Byler of Google contributed low overhead heap profiling. Finally, that brings us to JDK 12. Still in development, the first release candidate build will hopefully be tomorrow, this week, tomorrow, Thursday. There are 8 JEPs in JDK 12, including a micro benchmark suite for the JDK itself, a preview language feature, switch expressions, and various VM performance improvements. Again, Oracle engineers did most of this work, but in JDK 12 we do have an entire new garbage collector, Shenandoah, contributed by Christine Flood, Roman Kenke, Alexei Shibilev, and others at Red Hat. If you'd like to test out JDK 12, especially once we have the release candidate build, hopefully tomorrow, you can get it here, download it, test it. If you find something wrong, please let us know as soon as you can. So as you can see, what has changed is not the rate of innovation. We continue to innovate at a regular pace. What's changed is the rate of innovation delivery. We can now deliver every 6 months. In 3 years, by 2021 or so, we probably will have merged around 90 JEPs, just as we had in JDK 9. These feature releases aren't just about JEPs, of course. Each contains many smaller enhancements and, of course, bug fixes. As an example, according to our bug database, in JDK 11, we resolved almost 2,500 issues. Oracle engineers were responsible for most of these, but there were significant contributions from engineers at SAP, Red Hat, Google, Bellsoft, and a smattering of very productive individuals. Returning to our timeline, the 6-month cadence will enable Java to compete better with other platforms, but you might be wondering, what about updates, security fixes, critical patches? The plan in the OpenJDK community is to update the current feature released for at least 6 months. That is 2 quarterly update releases. And then every 3 years, we'll declare a long-term support release. JDK 11, shipped this past September, is the first long-term support release. The next will be 17 in 2021. If you like, you can imagine JDK 8 way up there to the left as the previous long-term support release. Each of these LTS releases will be updated well past the beginning of the next LTS release, and possibly even longer. Now, you might think that LTS releases are in some way experimental. Oh, they're just fancy beta releases, but they're not. Every release is production ready. What differs is only the support timeline. So, you have a new kind of choice to make. You can take the blue pill or the red pill. You take the blue pill, you wake up in your bed and continue to develop and deploy uncomfortable, conservatively managed, slow-moving LTS releases with an update release every quarter and a major migration every 3 years. You take the red pill, you go down the rabbit hole, where you can enjoy the latest language features, API enhancements, performance improvements, and bug fixes with a minor migration every 6 months. It's up to you. All I offer is the truth. If you do choose the LTS path and take the blue pill, you might be wondering, who will produce your update releases? Again, you have a choice to make. Since JDK 9, Oracle contributors in the OpenJDK community have focused and will continue to focus primarily on feature releases rather than on updates. Oracle will ship OpenJDK builds under the GPL for the first 6 months of each feature release. That's the GA release plus 2 updates, whether the release is a long-term support release or not. After that, Oracle will offer long-term support builds, but in a change from the past, these will be available only under a commercial license that allows free use for development and testing, but requires payment for use in production. That might sound scary, but don't worry. Java is still free. All of the code is still available under the GPL for anyone to build, test, publish, update, and support. Oracle engineers won't regularly contribute to, or much less lead LTS releases as they have in the past. That's okay. The OpenJDK community as a whole has a proven track record of transitioning the leadership of update releases from Oracle engineers to non-Oracle engineers. We did that years ago for JDK 6 and JDK 7. We did it again for JDK 8 just last week when Andrea Haley of Red Hat took on the leadership of the JDK 8 updates project. We're already in the process of doing the same for JDK 11. This isn't just my personal fantasy. As Andrew Haley has assured everyone, whether by Oracle or Red Hat or someone else, JDK LTS releases will continue to be supported. We all have a lot invested in Java, and we won't let it fall. So the LTS work will carry on in the OpenJDK community as it has in the past. You'll be able to get carefully built, well-tested JDK LTS builds based upon all that source code in most any Linux distribution, whether it's derived from Red Hat Debian, Gentoo, or Arch. If you're not on Linux, you'll be able to get LTS builds for free from a variety of providers. For this plan to work, it's critical that you be able to switch from one provider to another. In past releases, that wasn't possible because Oracle always held back a few so-called commercial features that were available only to paying customers. These included application class data sharing, Java Flight Recorder, Java Mission Control, and the Z garbage collector. To enable such switching and to establish a level playing field across all providers over the past year, Oracle open-sourced all of these commercial features so that Oracle builds and OpenJDK builds are functionally interchangeable at this point. You can switch from one provider to another as you please. But when you choose a provider, you might want to consider those with the depth of knowledge that comes only from a long-term investment in the platform. You have a choice. You can take the blue pill or the red pill. You can choose the conservative LTS path and take the blue pill with a major migration every 3 years. This can be a fine and appropriate choice for conventional enterprise-style deployments of large applications on large servers. Or you can choose the aggressive feature release path and take the red pill with a small migration every 6 months. This can be a good choice if you're deploying to the cloud or to app stores. If you choose the LTS path and take the blue pill, then you shouldn't ignore the non-LTS releases. Some free advice. If you maintain an infrequently migrated system, then you should still test it with each non-LTS release. That way you'll be nearly ready for the next LTS release by the time it's available. You will have spread out the migration work over time. If, on the other hand, you choose the adventurous feature release path and take the red pill, then you're going to migrate to each feature release as it becomes available every 6 months. So make sure that your tools and dependencies can keep up. Many will be able to keep up, but some won't, especially if they're no longer maintained. So plan with care. To sum up, we are evolving the Java platform at a faster pace. We're doing this in order to keep up with competing platforms. We have broken a few things and will continue to do so in order to make Java a better fit for modern applications. Are these changes really all that scary? No, I don't think they are, for 4 main reasons. One is that we will always give advance notice before removing anything, and we'll only do so when there's a very good reason. We don't want to break existing code unnecessarily, because compatibility remains one of the core values of the Java platform. Second, you have a choice to make, which you didn't have before. You can take the blue pill and migrate every 3 years at a comfortable, stately pace, or you can take the red pill and enjoy the latest features and fixes every 6 months. It's up to you. Third, it's true that Oracle will no longer provide free long-term JDK updates, but Java is still free. Free updates will be available from a variety of other providers, including all of the major Linux distributions. If you want active support, someone you can call when something goes wrong, then you're probably going to have to pay someone or else do it yourself. But that's always been the case. So choose your provider wisely. Finally, we did break a few things. Migrating past Java 8 may require some work, but it might not be as hard as you think. All 3 of the major IDEs already support essentially all of the new language features. Many popular tools, libraries, and frameworks already support JDK 9, if not JDK 11, or even JDK 12. You don't have to take my word on this. As you might recall from last year, just after Java 9 was released, I asked on Twitter, Do you maintain a popular Java library, framework, or tool? If it works fine on JDK 9, then please reply with its name and version. That, of course, was a year ago, well, a year and a half ago now. So shortly after JDK 11 was released, this past September, I asked, do you maintain a popular Java library, framework, or tool? If it works like heaven on JDK 11, then please reply with its name and version. My thanks to Sam Brannon of the JUnit team for that hashtag. There were many, many responses to these tweets. All 93 of these libraries, frameworks, and tools work just fine on JDK 9. They either worked without change, or in some cases their maintainers had to fix them, and in many of those cases the fixes they had to make were pretty straightforward. These include the build tools, Ant, Maven, and Gradle, test frameworks, JUnit, TestNG, popular libraries, ByteBuddy, Jackson, Log4j, Hibernate, Juke, Netty, and the entire Spring framework is in there. 51 of these components work not just fine on JDK 9, but like heaven on JDK 11. Since the transition from 9 to 11 is much easier than the transition from 8 to 9, I expect that the rest of them will catch up in short order. My most urgent advice to you today then is this. If you're using Java 9 or later, upgrade to the latest versions of all your tools and dependencies, because everything changes and nothing stands still. Don't believe a word I've said. Thank you very much. Okay.
Thank you, Mark.
Thank you.
Thank you very much. So we'll just do a quick shift here. So while we're doing this, I have a few of those Jfokus beanies. If anybody wants them, there is one. There is. See if I can make this. We have to spread the. Over there. Oh. If you're that eager. All set? So then finally, we will get the answer. Functional programming or object orientation. Please welcome Brian Goetz to this presentation.
Thank you, Mattias. So this is a slightly more philosophical talk, and this is about the sort of fictitious divisions that we invent for ourselves and how they sort of can harm the progress of our industry. So in this talk, I want to explore one particular fictitious division, which is the tension between OO and FP, and make an argument for why and how we can and should do better. So I love functional programming, and after a long time in the shadows, it's kind of started to peek into the mainstream, which is great. But I still believe that mainstream wide-spectrum languages like Java, for example, have even more to offer us in terms of applying functional techniques to real-world problems than the purely functional languages do. And as a language designer, one of the reasons why I work in Java is there's leverage there. There's an old joke about the famous bank robber, Willie Sutton, when they asked him, how come you rob banks? And he says, well, that's where the money is. And languages like Java are where the users are. So if we want to help people be better programmers, the place to start is to go where the programmers are. Now, some people might say that I'm not qualified to give this talk because I have this conflict of interest. Java is an OO language. I'm a Java guy. And that's fine. Developers often have strong opinions about things they don't know anything about. So I'll ask you to indulge me while I do a bit of the same. So I'll start with a topic about which I know really nothing, but I'll talk about anyway, very briefly, which is sports. And in particular, I want to talk about the social dynamics of sports and sports rivalries. So, for example, in the United States, one of the biggest rivalries is that between the New York Yankees and the Boston Red Sox. And, rivalries are an essential part of sports. Every team needs a rival team, and the fans, they might love their team, but they love to hate the rivals even more, right? So imagine a typical New York Yankees fan and a typical Boston Red Sox fan. And these, two guys actually have quite a lot in common, right? So let's put this in the context of some object-oriented modeling. They're both people. They both share the behavior that people share, like drinking beer. And, they're both sports fans, so they both, like to do the wave and spout statistical gibberish. And, they both hate the other guy. So, in a lot of ways, they're really the same person. And certainly from the outside, if you're not a sports fan, they certainly look like exactly the same person. So, this concept about, differences that you can only see from the outside, is well covered in the geek canon. So, for example, you remember that Star Trek episode where the crew encounters the species of half black, half white humanoids, and some are black on the left and some are black on the right. And of course, they hate each other and they're locked in a bitter civil war, and there's only two of them left and they're still trying to kill each other. But like the sports fans from the outside, these guys kind of look like the same guy. But all they could see is how they were just like complete opposites, right? And so, of course, this was about as subtle as a sledgehammer. But, we play this game out every day in the way we work, right? So imagine what we look like to normal people when we're arguing about spaces versus tabs. Or text editors. From the outside, to our, husbands or wives, we must look ridiculous, right? Because the spaces advocate and the tabs advocate are really indistinguishable. They're just opinionated geeks, and yet they're ready to kill each other not only over code, but over a completely non-functional aspect of coding. And meanwhile, a normal observer would be thinking, if these two could just get over their stupid argument and learn to work together, then maybe my car could actually talk to my phone. So this brings me to another subject about which I know nothing, which is cultural anthropology. When a sports team wins, what do the fans say? They say, "We won," even though they contributed absolutely nothing to the winning. And, this is because we're naturally wired to form tribes. And tribal identity has a sensible evolutionary basis. It's a natural defense against starvation or being eaten by tigers. There aren't very many tigers roaming the streets of Stockholm these days, or at least not that I've noticed. But our brains have taken a little bit of time to catch up with that. And, tribalism isn't all bad, right? That's how, we learn from members of our tribe, we help each other, we collaborate, those are good. But it's a short hop from let's, help the members of my tribe to let's demonize the members of the other tribe, rather than saying, well, what are we going to learn from them? And I'm sad to say that as programmers, we're bad at this. We're really bad at this. We're constantly defining our identities as we're Python programmers or C# programmers or functional programmers. And then we have unconstructive arguments about why the other is wrong or foolish for preferring those primitive tools. Now, as programmers, the more I program, the more I realize how much there is to learn. And we all have so much to learn about building correct, robust, maintainable, secure, easy-to-use, cost-effective software that we kind of should be ashamed and certainly not criticizing each other about tabs or VI or static types or actors or objects or anything. The user doesn't care whether the code was written in Haskell or Visual COBOL, right? They just want their phone to talk to their car, and that's actually kind of reasonable. So the tribal division that I'm going to talk about today is functional programming versus object-oriented programming. It could just as easily be static versus dynamic typing or managed versus native or any number of other fictitious divisions we can invent. But these days, functional programming is popular, and so, not surprisingly, it's also popular to hate on object-oriented programming. And so it's easy to find blogs or talks about how OO has failed to live up to its hype. Okay, well, that's totally true. It has failed to live up to its hype. But realistically, has there ever been a programming technology that has lived up to its hype? The critics of objects, they have a standard playbook. They take an example of object-oriented programming done badly, and then they jump from, well, it didn't work here, to it must not work at all. And to be fair, they have plenty to work with. There's lots of examples of object-oriented programming done badly, but that doesn't mean there isn't something to learn from it. So while these rants might have a point, they assume a false dichotomy. Their argument rests on, if my tribe is right, the other tribe is wrong. But OO doesn't have to be wrong for FP to be right. We all have the things we can learn from both of them. And that's really the main theme of this talk today, which is, rather than investing so much in thinking of ourselves as being Python programmers or C++ programmers, we should care more about becoming better programmers. We all have so much to learn. We should seek to learn as much as we can from as many paradigms as we can. So to become better programmers, my advice is, go learn classical functional programming, go learn classical object-oriented programming, and then strive to rise above them both. Okay, so what does that mean? That sounds good, right? What does it mean? Languages and paradigms are tools. And no tool is ideal for all situations. So the French philosopher Émile Chartier once said, "Nothing is more dangerous than an idea when it's the only idea you have." If we only have one paradigm, we're going to use it in the right times and the wrong times. We'll use it when it doesn't fit, or we'll try to distort our view of the problem into one that fits, because it's the only tool we have. Whereas a programmer who is comfortable in multiple paradigms is far more likely to find a better solution for any given problem, regardless of what language that they're using. The right solution is probably not pure OO or pure FP or pure anything, because it kind of has to be. Each of these paradigms makes strong assumptions and focuses on one part of the problem. Pure functional programming, for example, has no notion of computational resources like memory or threads or file handles, and pure OO has no notion of a computation that isn't localized to some component. But of course, every real-world problem has to deal with file handles and memory and non-localized computations. So we need, at least minimally, to learn something from each of them. So it's easy to criticize OO. Some of it's deserved, some of it isn't. OO arrived on the scenes under tremendously inflated expectations. So by 1990 or so, which is, I guess, before a lot of us started programming, I guess before some of us were alive, the hype surrounding objects really had reached absurd proportions. So most of the OO code out there is kind of what I would call Sorcerer's Apprentice OO, which is you take sensible principles and then you apply them to the ridiculous extreme. So for example, if encapsulation is good, more encapsulation is better, right? But realistically, that's not what you want, right? You may want a heavy lock on the front door, but you really probably don't want one on the bedroom closet. But like most OO code treats, family members and burglars with about the same degree of distrust. And, just in case that wasn't bad enough, we tend to draw the boundaries before we even know what the house looks like, right? And so you get the equivalent of, a bank vault door on your bedroom closet and, just for good measure, one in the middle of the hallway also. Now, of course, this isn't what OO is about, but, for some people, it's what comes to mind, and I think to some degree we did this to ourselves. One of the worst offenders is the original Java Beans convention, and this was designed for a particular purpose: dynamically discoverable visual components in an interactive editor, which was a perfect application for OO. But, the costs and benefits of any given technique are contextual, and they don't apply everywhere. But, the Learn Java in 21 Days books told us, yep, do this everywhere, getters and setters for everything. So we got the worst of both worlds, like all the ceremonial overhead and friction without the abstractive value. Nice going. So, when people think they're criticizing OO, they're really criticizing a sort of cartoon exaggeration of OO. And the conventions that might be right for a graphical component framework might be silly for most domain objects, but that doesn't mean the technique is silly. And of course, it's fun to criticize things that are popular, and sometimes it's therapeutic, but if we get too invested in these criticisms, it just makes us worse programmers because it's closing us off to what we have to learn from the other tribes. So if that's not what OO is, well, what is it? We have to step back from the details of your favorite language, C++ or Java or C#. And Alan Kay once said, I made up the term object-oriented, and I can tell you that I did not have C++ in mind. For example, most popular OO languages today emphasize inheritance. But class-based inheritance isn't necessary to OO. It's just one way to get polymorphism. Similarly, static typing. Most of these languages are statically typed, but Smalltalk was dynamically typed. You can have dynamically typed objects. The essence of object-oriented programming is that computation proceeds by objects sending messages to each other. And those messages don't have to be statically typed or synchronous or even local. You send a message to an object, and it does something in response. Maybe it performs a side effect. Maybe it sends you a message back. Maybe it sends a message to somebody else. And this structure of communication implicitly gives us polymorphism, because the only thing that's defined is the messages that you pass between each other. And so each entity in the system is able to respond, in any way that meets the needs for that message. And so we can get polymorphism from a lot of ways. We can get it from classes or from prototypes or from nasty stateful logic, but that's really just a matter of bookkeeping. But the commonality is that complex systems do need some form of dynamic dispatch, and most OO languages make this pretty easy to express and reason about. Similarly, with respect to state, in OO, state is owned by objects. So to access an object state, you send a message to that object. And that brings us to the other major contribution of classical OO, which is encapsulation. OO languages give developers a straightforward way to say, this is my state, only I can access it. And if you're old enough to remember what procedural programming was like when that was the dominant paradigm, one of the biggest impediments to program scale was the reasoning about program state. Because if all the code can access a variable, then in order to reason about possible values or refactor, you have to analyze the whole program. And encapsulation lets us turn this global analysis into a local one, which in turn frees us to build larger programs without getting mired in complexity. OK, so that's OO. What's FP? If you ask people what the essence of FP is, you'll get an answer like immutability in pure functions, or maybe pure functions as first-class values, or maybe function application by substitution. And these are all sort of good mental models, but in reality, most functional programming languages don't actually behave this way. And with good reason. Simulating state and I/O with monads is very cool. It's cool that you can do it, but it's not how most people want to program, and it's nearly impossible to reason about things like memory utilization. So most functional languages make some practical concessions towards the messy real world with some direct support for I/O and mutation, and they accept the strictness that entails, and then we rely on programmer discipline not to use those when they could be avoided. OK. So compare. Computation proceeding by sending messages to objects, computation proceeding by applying functions to values. Scaling up, in each of these paradigms, what's a program? An FP program is really just a big function, and functions have a simple role. They transform inputs to outputs. In OO, there's a sort of more ambitious notion of a program. It's an executable model of some entity. And for any given situation, one or both of these views might be useful. So one of the things that you tend to see in functional languages is that ownership of data is kind of more distributed. You have a lower degree of encapsulation, especially in the dynamically typed languages like the Lisp family. Almost any code can inspect the innards of data that's passed to them. And OO makes much more of an investment in making opaque islands of data that's owned by somebody. And there are times when this encapsulation is a lifesaver for managing complexity and security, and there are times when it just gets in the way, and that's having the bank vault door in the middle of your hallway. So as professional programmers, we're going to encounter both of these situations, and we should know how to tell them apart and how to deal with each of them. So, you'll often people here say, well, in OO, everything's an object, and in FP, everything's a function. In fact, like every programming style has an obligatory, one sentence, everything is a summary. Everything is an object or an actor or a function or a peanut butter sandwich or whatever it is. And these characterizations are useful for about the first 5 minutes of learning a new paradigm. But overall, they tend to be pretty destructive, because not only isn't everything an object, but in reality, nothing is an object, and nothing is a function. And certainly not everything is a Java bean. Objects and functions, and actors, they're just models. They're models that are useful for helping us understand our code and our strategy for understanding the problem, but we have to be careful not to confuse them with representing reality. It's only a model. So we can choose to model things with objects or actors or functions with varying degrees of fit and fidelity in the hopes of managing the messy real-world complexity of the problem. But there's a big leap from use X to model Y to everything as an X. Everything as an object is wrong for two reasons, at least two reasons, the object part and the everything part. But, functional purism today is no more attractive than the OO purism was back in 1989. And so, we have to abstract things away from the real world in order to have any chance of solving them with software, because the world is so full of messy accidental detail that we have to find a way of filtering it out. But we have to keep our eye on the goal, which is solving a problem in the world, not a problem in our software. And to do that, we may very well need objects and functions and actors and maybe also peanut butter sandwiches. So, it's really easy to mistake our tools and our paradigms for reality, right? So in the real world, we have a problem to solve, like, I want to make a phone call from my car. And we decide, for good or bad reason, that the easiest way to solve it is to turn it into a software problem. So we have to transform our problem into a set of inputs that are going to be seen by a program, and a set of desired outputs that correspond to our goal. And then we write a program to turn the inputs into the outputs, and hopefully we're done. So there's some process by which we turn a real-world problem into a set of abstract software requirements, and then we can solve our problem in the more practical domain of software. And so we'll call this mapping F. And then there's an inverse mapping, F inverse, that maps back to the real-world space. And this is a perfectly useful way to apply what we know to solve problems in a more tractable domain, except that we often make this one big mistake, which is we assume that this F function and its partner, F inverse, is a homomorphism. In other words, that it actually captures all the interesting real-world structure of the problem, maps it to the software space, and properly maps it back. And the danger is information is lost in this mapping. And the more the mismatch is between our everything is an X model and the real problem we're solving, the more likely we are to get something where we have a program that transforms the inputs to the outputs, and it ticks all the boxes on the requirement sheet, but it doesn't actually solve the problem in the real world. And as programmers, of course, we're comfortable solving programming problems rather than messy real-world problems. We can easily confuse writing the program with solving the problem, so we shouldn't do that. In our more arrogant moments, we might even describe what we do as building abstractions for a living. Sounds pretty good, right? But abstraction is a double-edged sword. If you look it up in the dictionary, you'll find several definitions. It could mean reduced to an idealized form, separating away all the confounding details to reveal the essence of something. Well, that sounds pretty good. I'd like to be associated with that kind of abstraction. But it also means difficult to understand. And that's the kind of abstraction we think about when we look at other people's code, right? But, even the first is kind of suspect. Different details matter at different times and at different degrees when you're trying to solve real problems. So by necessity, the abstractions we use in programming are going to be leaky. And, we use these abstractions or tools to manage complexity and support reuse, but they're not an end unto themselves. They're tools to solve problems. So we have to continually ask ourselves whether our abstractions are serving the user and solving the problem, or whether they're mainly serving us. Because remember, the user doesn't care about their abstractions. They just want their car to talk to their phone. So, I like objects and I like functional programming. I know a lot of people who are saying that they're moving on from objects to functional. And, for a while that made me start to wonder, well, if I still like object-oriented programming and all these guys have moved past it, what does that make me, right? So I didn't really like that explanation, so I tried to come up with a better one. Now, I probably have a somewhat different experience of programming than the average developer, because most of the code that I write these days is platform libraries. And when you're working on platform libraries, you're on the other side of a lot of boundaries from your users. Maintenance boundaries, versioning boundaries, encapsulation boundaries, compilation boundaries, compatibility boundaries, security boundaries. You can't count on your library being co-evolved or co-compiled with its clients or its subclasses, because they're maintained by different groups of people. You want to hide your internals, so you have the freedom to evolve your implementation separately from your clients, and sometimes because you have security constraints to enforce. And in a dynamically linked platform like Java, this happens so automatically that we don't even notice. That as long as you've evolved your library in a responsible way, you just drop a new jar on the class path and it all works without recompilation. OO languages are great at boundaries. They give us tools for precisely defining, navigating, and defending those boundaries. So it stands to reason that OO is at its best when a code base spans boundaries. And platform libraries are a great example of this. Sometimes even artificial boundaries are helpful just so that they can help us manage the complexity. So they limit the required scope of analysis or deployment to a small region of code. The more my client binds to my data representation, the more I have to more code I have to audit when I want to make a change. So this is obviously a big deal for security, but it's also a big deal for correctness as algorithms get more complicated. So as an example, take concurrent hash map in Java or the fork join pool scheduler. So these are both examples of really, really tricky code, subtle representational invariance. So it's really a good thing that the clients not only don't have to, but actually can't try to reason about the representation. They just use the services of the API. So you might be thinking, okay, that's great for you. You write platform libraries. I'm an application writer. What does this do for me? Now, the benefit's more indirect, but it's no less real, because as we evolve the Java language, one of the considerations we ask ourselves is, will this change enable expressive new library idioms? Because if you make it really easy to develop and distribute robust libraries, you get a richer ecosystem, and that means application developers have a bigger variety of high-quality libraries to choose from. And this is true not just for applications, but for languages as well. I mean, so think about, why did Scala or Clojure choose to target the JVM? Well, where would Akka be without the fork join pool? There's a huge ecosystem of libraries that they can just leverage. And so the richness of the ecosystem benefits everybody. So on the topic of boundaries, I have kind of a favorite talk that I like to recommend on the subject, which is called Big Surprise Boundaries by Gary Bernhardt. And in it, he talks about how to balance the use of OO and FP in one system. And he points out that within a closed domain, the functional idioms really win because we don't have any needs for boundaries. But as we approach the parts of the system that deal with messy things like other code, I/O, state, failure, communication, the strength of objects starts to dominate. So this diagram is meant to suggest this separation of you have the functional entities in the middle, which are little circles, and then the outer shell is what's dealing with the nastiness of state and I/O and failure, and it's your interface to the outside world. And the considerations at the boundary are very different from the considerations on the inside. On the inside, you control the code, it's recompiled together, there's no boundaries, it's maintained by the same people. Across boundaries, you're thinking about validation, defensive copies, failure management, separate compilation, versioning, security, migration compatibility. And these are wholly different considerations. So sometimes this shell is code that we write. Sometimes it's part of your runtime. I mean, this diagram could describe an Erlang actor, right? Within the actor code, everything is pretty and clean and functional. But between actors, there's a lot of messy stateful stuff going on with message queuing and retrying and failure. And it's easy to think of Erlang as purely functional because all the messy stuff is hidden inside. But it's in there and it's imperative and it's messy. So Erlang's actors are really like classical objects. In fact, they're more like Alan Kay's vision of objects than what we find in C++ or Java. And you can make a similar argument about microservices, right? Within the service, you can use functional idioms really well, but at the boundaries, you're dealing with I/O and state and failure, and that's anything but functional. So it's kind of amusing that in our desire to move beyond objects, we kind of keep reinventing them and just giving them new names. So a small program might be represented as one instance of this pattern, but it might make sense to represent it as a network of cooperating shells. And so in designing systems, an important architectural question is, where do we put the boundaries? And you could put that another way, which is, what are the objects? Not the low-level implementation classes in Java or C++, but the classical OO objects, the independent entities that communicate with each other by sending messages. So I think we're starting to see what it means to rise above both OO and FP. Use them at different granularities. Use OO modeling to find the right places in your application to put boundaries. Use FP techniques within those boundaries. And you can do both of those in one language. one of the big complaints about OO is we have too many boundaries, we use them when we're not needed. But one of the things that OO has to teach the functional world is sometimes putting boundaries between you and yourself is one of the best tools we have for containing complexity. So functional programmers like to tell themselves that FP is an evolutionary advance over object-oriented programming. But, this is kind of like tribal think, right? And in a funny way, the trend towards FP is also kind of a step backwards in this same progression. And if you think about the conditions under which OO came up, the world was procedural. We had no language support for encapsulation or dynamic dispatch, but we were smart. We were able to simulate them with function pointers and programmer discipline. But the result was inevitable. Clients would end up binding too tightly to their data representation, and ultimately that put a limit on how much our programs could scale. So FP offers us way more than Imperative did in the way of behavioral abstraction. But when it comes to data representation, a lot of FP languages kind of take a step backwards into that procedural world. And the temptation is there for the clients to take the data apart directly, and the same risk of limitation of scale is present. And I don't think it's accidental that the biggest FP programs are much, much smaller than the biggest OO programs. And that's not because functional languages are so much more expressive. A more cultural way in which the trend towards FP is a bit of a step backwards is how it acknowledges and talks about real-world complexity. This was an observation made by Brian Marek about the sort of culture of documentation in language communities. Writing about FP languages tends to leave aside the messy real-world problems from their documentation and samples, whereas a lot of writing about OO tries to meet the complexity head-on to show how these mechanisms contain real-world complexity. And I think it's because functional programming is sort of singing us a siren song that makes us want to believe we can make the real world as neat and tidy as mathematics, which, don't get me wrong, I would love it if that was the case, but we can't do that. So we need to rise above our desire for things to be cleaner and simpler than they are and engage the complexity head-on with all the tools we have for the job. So once we let go of this tribal belief that one is better than the other, it's possible to get the best of both worlds. FP is great when you're dealing purely with data. And inside, the functional core of a lot of programs, it is all just data, and they're all living on the same side of all the boundaries. Similarly, OO focuses on modeling of active entities. And so it's really good in system components that have to mediate between the program and the outside world. And we get to rise above because both of these offers us complementary tools for managing the complexity. And complexity is really the name of the game. We are awash in a sea of complexity. Some of it is inherent, some of it is accidental, and the central goal of programming language design should be to give us tools for managing complexity. And the fact that there's so many languages out there illustrates that complexity comes in a lot of shapes and sizes, and no one paradigm is going to be perfect for all of it. The reality is that we're always going to be operating at the limits of our ability to manage the complexity. Because think about the last time you rebuilt a system. A better technology comes along, it promises that you'll be able to scale better without being overwhelmed by the complexity. So what do we then do? Well, we rebuild our world in the new image, and we hope it's going to take us back to a lower complexity world. But then the next thing we turn around and do is we immediately build a bigger system. And we build until we, again, hit the threshold of where we're able to contain the complexity. Once one limiting factor is removed, another one emerges. And the cycle of hype and disappointment spins again on us. And it really can't be any other way because the economic factors are always pushing us towards building bigger and more powerful systems. So as a community, we've discovered basically one trick in the last 40 years for managing complexity. It goes by multiple names. You could call it divide and conquer. You could call it composition. It's the same either way. And in that big list of things that everything is not, they all claim their secret weapon is composition. Functions compose, objects compose, actors compose. The reason is none of these paradigms own composition any more than any one language owns garbage collection. This is the fundamental technique we have for managing complexity. So they both guide us, both OO and FP guide us towards divide and conquer, but from different directions and at different granularities. OO takes kind of a top-down approach. It encourages us to draw the encapsulation boundaries so that we can replace global analyses with local ones. FP encourages us to build upwards, compose simple building blocks into bigger building blocks. Obviously, one works better in the large, but gets in the way when you try it in the small. The other kind of shines with composition in the small, but its minimalism can often constrain its ability to scale. So the false dichotomy of functional versus imperative or versus object is kind of related to another false dichotomy, which is, should programming be more like math or like physics? Now, as a mathematician, I have my own personal opinion. And I like this comic because it feeds my sense of confirmation bias. And I suspect a lot of functional programmers might feel the same way. But it's really easy to be seduced by the math and lose sight of the fact that we're always running on a real machine. We ignore that at our own peril. Registers are not immutable. Down in the hardware, everything's mutable. So functional languages give us a nice illusion. But down in the real world, at the machine level, it can be ugly. Functional languages kind of disavow any notion of resources like memory or threads or files, and this makes resource management entirely the job of the runtime, which can be a good thing. We can focus entirely on our problem and not be distracted by the bookkeeping, but sometimes it doesn't give us the resource efficiency we need to solve those problems in an economically feasible way. Imperative languages come at it from the other direction. They start with the physics and they work up towards the math, and this gives us more control, but also more temptation to get mired in the low-level details. So, immutability is great for modeling business data, but it does considerably less well down at the data structure level, right? Most data structures are basically resource management concerns. And functional languages offer us exactly no help with resource management. Almost all classical data structures are based on mutability because it gives us cheaper resource reuse than destroy and create does. And without mutability, we lose like cheap updatable hash maps, and that's our only trick for reducing O of n problems down to O of 1 problems. And like I said, the immutability is just an illusion. The hardware is always mutable. So, don't get me wrong, functional data structures are really cool, but they're sort of the dancing bear. It's not impressive that the bear dances well. It's impressive the bear dances at all. So, if we think that programming is basically math, we risk ignoring the real-world resource considerations. If we think it's basically physics, we risk ignoring computational abstraction. But we don't have to choose. We get to play in this whole space in the middle, and we should be happy about that, right? We need both. We should be comfortable in both, and we shouldn't hide off on one side because the light is better there. So, okay, we get it. Narrow viewpoints are bad. How do we get past our tribal perspectives? We can start by not letting our tools narrow our thinking. We can try to avoid having our models become our reality so that we can shift between the influences of OO and FP as the needs arise. So, in this way, I think the pure FP languages are going to have a very rough time competing with broad spectrum languages like Java that offer reasonable support for both paradigms. And, that doesn't mean we have to stop doing FP. It just means the language isn't going to force us to do it. We have to make a deliberate choice. And single paradigm languages, those everything is an X languages, they force us to wedge everything into their paradigm. So the reality is most languages are built on top of something else. And sometimes you have a problem that you can't solve in the main language. You have to drop down into the substrate language. Often this happens when implementing core libraries. You can't write Erlang's message dispatch in Erlang. You can't write the IO monad in Haskell. You can't even write socket input stream in Java. And so language implementers, they're willing to do that, right? Like our JVM guys like to say, we code in C++, so you don't have to. But when users have to drop down into the substrate, that's usually not so good. And a narrow spectrum language gives you kind of a bad choice. Either split your program across two totally different programming models with a big nasty barrier in the middle, or do without the things you can't do in the hosted language. In a successful broad spectrum language, you can write more of the platform and the libraries and the applications without crossing that barrier. It's really powerful that we can write concurrent hash map in ordinary Java code. And that means, among other things, that we're going to get libraries like that, and we'll get more of them than if they had to be written in native code. It also means that users that have specialized needs can just take this code and customize it as they see fit, and abstractions like Akka can just use it. At the same time, languages like Java and C# are getting pretty good at learning tricks that had previously been the domain of functional programming. 20 years ago, it might have been garbage collection. Now it's lambdas, coroutines, pattern matching. And despite their historical associations, these features have nothing intrinsically to do with functional programming at all. It turns out they can fit very nicely into OO languages as well. In his keynote at JuliaCon called Lessons Learned from Fortress, Guy Steele pointed out that good ideas survive by hopping from one language to another. The language that develops the idea may not be the one that survives or popularizes it. It may very well be a completely different language. So it doesn't matter what language you're working in. No one can stop you from doing functional programming in your head. So just summing up, we all have so much to learn. The problems that we're trying to solve with software are so messy that we can't afford to ignore anything we can learn from any paradigm, programming paradigm. And we certainly can't lock ourselves into a single paradigm because we like it better. We need to learn from functional programming, we need to learn from object-oriented programming, and from others too, and we need to rise above them all. So don't be a functional programmer, don't be an object-oriented programmer, be a better programmer. Thank you.